Hello, this is Bob Lessig in the Center for Biotechnology Education at Johns Hopkins. In this lecture, we will examine the e-value and why the e-value is important in answering questions about homology. Our main objective is to be able to explain and interpret the e-value that you get in a database search. And then recognize that the e-value, the lowest e-value or the strongest e-value, is going to be the best match, and that's going to be at the top of the output in a BLAST search. What exactly does the e-value mean? We will examine two elements: rarity of achieving a particular score and the size of a search database. And then calculate that e-value based on the score in the search space. If the score is high enough relative to the search space, you will get a strong e-value. If I say I scored 10 points without any context, then it's pretty meaningless by itself. Yahtzee is a game involving throwing dice. It's pretty easy to get 10 points on a single turn, and often game scores go above 100. Now in basketball, that's a pretty decent game. It's harder to do, but possible. Foursquare is a phone app. You get points for checking in on your phone at particular locations. To get 10 points is a lot, but it happens from time to time. In lacrosse, 10 points is more rare. It's a game in which points include both goals and assists. It's a lot harder to get 10 points in lacrosse than in basketball. It happens, but it's rare. Now in soccer, it's almost impossible. Teams rarely get 10 in a game. For an individual to achieve 10 points, even counting assists, just doesn't happen a lot. The point is that you need context. The scoring system also matters. If they gave every team 5 points for a goal in soccer, then scoring 10 points is not as hard. So when we think of points in terms of an alignment score for a pair of sequences, then we have to ask, how hard is it to get that score? Many of you may be familiar with these big lottery jackpots. In the United States, often many states get involved and sell tickets to make the jackpots really high. So if you bought one ticket, and you have a win probability of 1 in 10 million, you will probably lose. The odds are heavily against you. But what if 20 million tickets were sold? Now the chance of someone winning becomes very possible. With 20 million tickets and a win probability of 1 in 10 million, then on average, we should expect 2 winners. That is multiplying 20 million times 1 over 10 million. Since we should expect, on average, 2 winners, that is our expect, or e-value. The number of events, in this case the number of tickets sold, clearly matters in this formulation. Okay, so what does this mean for BLAST? A BLAST search starts with a single sequence and attempts to find related sequences in a very large database. Each match is given an alignment score. We can look at the highest scoring sequences in the database and ask the question, how rare is that score? Well, remember, your scoring system matters. The substitution matrix determines how many points to add or subtract for each match or mismatch. There are also gap penalties for gaps in the alignment. That matters too. A lower gap penalty will give you higher scores because you're not penalizing as much. Now, suppose one sequence gives you a very high score. You determine that it's very rare to get a score that high. But as with the lottery, you are searching a database of millions of sequences. That's a lot of events, and sometimes you get a high score by pure luck. Let's put it this way. Suppose you get a score that is a 1 in a million event. It's hard to get a score that high. But suppose you search 2 million sequences. By luck, we should expect 2 scores to be that high. Doesn't seem so rare now, does it? In BLAST or any database search, each sequence is going to be aligned and has a match score. That match score is a raw score that's based on the substitution matrix, the matches and the mismatches, and the gap penalties. First, let's examine the number of events. As we saw, that matters. That is the database size or the search space. Now let's see how rare your match score is. For instance, if the score is 210 bits, the first question you ask is, what is the probability of getting a score above 210? So in other words, how hard is it to get 210 or more? The e-value represents the likelihood, given a number of sequences in a database, that you will get a score at least as good as the score you received. So probability is multiplied by the size of the database and then allows you to get the e-value. We'll look at a calculation a bit later. Now let's not lose sight of the goal of a BLAST search. With BLAST, the goal is to find related sequences within a large database. In many cases, homologs, which are sequences that share a common ancestor, have sequence similarity that leads to high alignment scores. However, we saw that unusually high scores can be attributed to luck in a very large database. So to determine homology, we want to make sure that luck is statistically unlikely. In other words, we're looking for scores that are so high that even with millions of sequences, we would still not expect to get scores that high. Now, before I go into the e-value map, let's take a look at a famous problem that is given in many college probability courses. It involves all the monkeys in the universe and a lot of keyboards. All the elements are given as part of the problem. Number of monkeys, number of keystrokes per minute. It's a large calculation. Question 1 is, what is the probability that a single monkey will type the word Hamlet? There are variations, but Shakespeare is very popular in these problems. Question 2 involves the probability that one monkey could type Act 1, Scene 1 of Hamlet. That's a lot harder to do by pure luck. For the word Hamlet, there are a lot of monkeys. It is not surprising that one would come up with that 6-letter combination. It's actually a difficult combination, but there are a lot of monkeys and they all have a year. The e-value would be greater than 1. I would expect a monkey to have done this. The monkey may have been lucky. We don't know. Maybe the monkey wanted to type Hamlet. Now, for Act 1, Scene 1, that just doesn't happen by chance, even allowing for misspellings. The misspellings are relevant to BLAST, because remember, some amino acids are chemically very similar. In this case, the monkey was not lucky. That's really all we can conclude. Something was up. The monkey did not do that by chance. So, in BLAST, if the e-value is much less than 1, we can assume that it was not luck to get a score that high. The sequences are related. How much below 1 do we want the e-value to be? It's pretty conservative, but less than 1 times 10 to the minus 4th is a good cutoff with a very low error rate. If in BLAST you see an e-value less than 1 times 10 to the minus 4th, we confidently call that a homolog. However, if the e-value is greater than that, we make no conclusions. Just like the monkey who typed Hamlet, that high score may have been due to luck. But that score may have been due to sequence similarity between homologs. All e-value calculations tend to be reported in bits. Those are base 2 numbers. Think of them as powers of 2. Why? Because Stephen Altschul, the inventor of BLAST, chose to do it this way. For example, the number 32 is equivalent to 5 bits. That's because 2 to the 5th power is 32. Likewise, 8 is 3 bits, because 2 times 2 times 2 is 8. The e-value is n over s prime, where n is the search space in bits, and s prime is the adjusted score from BLAST in bits. Why adjusted? That's where the scoring system and gap penalties come into play, and I won't cover those equations here. For example, with a search space that has more bits than the score, search space is 35 bits, score is 32 bits. 35 bits over 32 bits is 2 to the 35th divided by 2 to the 32nd. Exponents are subtracted on division. Since 35 minus 32 is 3, that equals 2 to the 3rd, or 8. With a score that has more bits than the search space, let's say 2 to the 35th over 2 to the 42nd, that's 2 to the minus 7, or 0.078. As you can see, low e-values means that the score has more bits than the search space. Or, to put it another way, the rarity of the score exceeds the magnitude of the search space. Or, your score is rare, even factoring in millions of events, or database sequences in this case. So let's consider these factors in the e-value. How rare is your score? How many events or sequences searched? If the e-value is less than 1 times 10 to the minus 4th, and 1e minus 4 is another way of writing that, then your score is rare, even considering the database size. And when that happens, conclude that your sequences are related or homologous. Thanks.